All right, chemist. So this is going to be actually quite a short lecture. There's not going to be a lot of writing for you to do. Um, I don't want you to draw in all of these particle views. This is what we did in class today. And the key idea here is that we can represent the molarity of a solution or how concentrated a solution is visually. So this idea of like, if I say something is 2 moles per liter, what does that actually mean to you? And if I said we have two solutions, one is 2 moles per liter, one is 1 mole per liter, what is that? How is that different? So what you guys looked at today were these particle views where you had different concentrations of solution. So you should be able to know that this is the, whoops, this is the most concentrated, and this is the least concentrated. Now, you know, that's certainly not that hard to understand. I think if I gave that to, you know, somebody who is much younger, they could say, oh, this one on the left has the most dots. The one on the right has the least dots. But what you need to understand is in terms of concentration. Concentration, another way to think of concentration is this idea of number density. How many particles do you have in any given volume of solution? So this one on the left, you have 10 particles per square inch. Then you get cut in half each time, 5, 2.5, and 1 1/4. Now what I do want you to copy down in your notes is this idea of any sample cut out of the original particle view has the same concentration of dots per square inch as the large sample. So the key idea is concentration is uniform throughout a solution. So what does that mean? Well, here, if I cut this into quarters, I have the same number of dots per square inch in each of the 4 quarters. If I counted this out, I would see that it's about the same in each one. So, like density, right? If I have a small piece of gold and a huge piece of gold, the densities are going to be the same. With a solution, if I take a small amount of solution, or if I have liters of solution, that concentration is going to be the same. Certainly, I'll have more moles of stuff in the bigger sample, just like I would have more grams of gold in the bigger sample. But the concentration stays the same if I have a small sample or a big sample. So think about it in terms of Kool-Aid. If you mix yourself some Kool-Aid, and like a big batch of Kool-Aid, and you split it up into 4 cups, each of those 4 cups is going to taste the same because they have the same concentration of sugar. But in the big jug at the beginning, you just have more moles of sugar overall. The concentration is the same. You just have more stuff in the bigger sample. Okay. So that the key idea of this is that concentration is uniform throughout. So I do want you to write this down. I don't know how many of you are writing this down. You should be writing down the wrap-up because this actually helps you answer the summary question. So how can you convert from molarity to moles? So the relationship between moles of molecules in a solution and liters is a proportional one. So we're going to do this in the next lesson. We're going to talk about preparing solutions of a given molarity. The concentration of a solution does not change with the size of the sample. That is a big, huge idea. And in calculating the number of moles of particles in an ionic solution, it is necessary to take into account all the ions in the formula. So if I dissolve CaCl2, it's going to dissolve into Ca2 plus 2Cl minus. So really, if I put in 1 mole of CaCl2, I get 3 moles of particles. So this is the difference between ionic and covalent. So that's another key idea there. All right, that's all for now.